things that you might not have guessed as possible, but you can do it. Okay, so alright, so let's look at this. Alright, before we start, I should say that so hopefully all of you have met me by now with respect to the projects. So I know that at least a few have not, and they have not responded to my email. So I don't know. So if you are here, then you should come meet me. Okay. And also, when we met, I asked people to send me a short midway write-up where you kind of give a short summary of what you want to do. So this is more like a statement of purpose kind of a thing. Okay, so you basically say what you want to do. Most of you have not done this, but I would encourage you to do this even though it's optional, because there won't be many surprises there. Okay, because at least you know you're kind of on track and things like this. Okay, so yeah, so do this if you haven't done so already. Okay, and as everyone knows, homework 5 is due tomorrow. Okay, so hopefully all of you are well on your way to that. And yeah. Alright, so the last few lectures we've been looking at optimization, and we said that that's a different way to kind of solve problems. Okay, so we said, suppose you have a combinatorial problem, you can try to phrase it as an optimization problem, and hopefully you can solve that optimization problem, right? And we saw that very often the exact phrasing turns out to be difficult. Okay, so you have to phrase it as optimization. And usually you do it as some kind of a 0-1 optimization, and that tends to be difficult, so you then relax it, and that's what we said, you change the variables to actually lie in the interval 0-1. Sometimes you could change it to lying in arbitrary real numbers. That's what we saw at the very end last time. I also have a link to something you can read about that. Okay, so on the course webpage, you can find a link to more on eigenvalue relaxation. Okay, and the reason you do this kind of relaxation is to make the problem tractable. Okay, so usually you can't solve 0-1 optimization problems, but once you convert them into some kind of a relaxation, you can usually solve them. And we said that you can optimize linear functions with respect to linear constraints. That's the whole idea behind linear programming. So often we come up with what are called linear programming relaxations. And then we saw how you solve that relaxation, you get a potentially fractional solution, and you can convert that into an integer solution. And the hope is that you don't lose too much in the process. Okay, and this is what we call the relax and round paradigm, and it's a popular way to design approximation algorithms. And just to recap, we have done two examples of this. One was vertex cover, the other was set cover. If you don't remember the problems, it doesn't matter. So this is just these are more of an example to illustrate this paradigm of relax and round. So that's what we had seen. And one of the cool things we had seen last class is this notion of randomized rounding, where you interpret these real valued things that you get, some xi's that were supposed to be 0-1. Now you get xi's in the interval 0-1, you interpret them as probability. And you round to 0 or 1 with a certain probability. Okay, so that was, we call that randomized rounding. And so this is what we had seen last time. Okay. So today we're going to switch gears, as I was saying. So we're going to talk about a different kind of algorithm, and so you will see what the main difference is. Okay, so these are called online algorithms. Online has nothing to do with internet or anything, so this is just things arriving one at a time kind of thing. Okay, so that's what we mean by online. And the general kind of motivating question is, can you design algorithms when you don't know the input fully? So, and this because this kind of a situation arises a lot in applications. Okay, and what do I mean by input not fully known? So let's look at some examples. So one of the canonical examples is caching. So actually, how many of you don't know what caching is? People don't have math background perhaps. Or do they also know about caching? Okay, so caching is this problem where you have a huge disk space and you have a small cache which a CPU can access very quickly, and each time you want to access a certain memory element, and you either have to fetch it from the disk or you can get it from the cache. So I'll go to that in detail. Okay, so hopefully all of you have seen some kind of caching. But the point here is that you don't know the requests ahead of time. Okay? So you keep getting these requests for serving some memory pages, but you don't know what requests you're going to see in the future. Okay? And you've got to make decisions based just on what you have seen in the past. Okay, so that's the general issue with online algorithms. Okay, so let me skip the allocation of machines. Let me talk about hiring secretaries. Okay, so this is another thing that all of you can easily relate to. So suppose you have secretaries arriving. Each secretary has a different skill level, let's say. You just have secretaries arriving one by one. At each step, you've got to make the decision whether to hire or fire this person. Okay? And you just have a history of the past. Okay? So now if you wait too long, you might actually, not hire anybody in the process, you might lose on good people. Okay? So this is the usual problem with hiring. Right? So you don't want to wait too long, and you also want to hire people who are good. Okay? So this is a typical example of an online problem. Okay, so you have people arriving one by one to make instantaneous decisions, and you've got to be able to, be happy at the end of the day. Okay. So the same is true with predicting stock markets. Like you have a particular stock, you want to figure out whether to keep it, buy it, or buy more or sell a little bit, okay. And you don't know what's going to happen in the future. Okay. And you want to, in some sense, make sure you don't do too badly at the end of the day. Okay, so these are the kind of things which people look at in the context of online algorithms. Okay, so I'll give brief examples, but there's this general notion here. So this is what I mean when I say that you're trying to design algorithms without fully knowing what the input is. Okay, so the input kind of arrives one at a time. You've got to make decisions, and let's see what the goal is. Okay, so we'll get to that in a bit. But so let's look at the example of caching in a bit more detail, okay, because this is what we'll do today. Okay, so you have, assume you have some memory, which you think of it as being infinite, okay, and you have your CPU just sitting here, and you have a cache that is sitting in between. Okay. And the CPU has like very fast access to this cache. And the cache has size k. It can store, let's say, k units of information. Okay. Usually they refer to these as pages. Okay, so the cache has space for k pages. The memory has a whole bunch of pages. Let's suppose every page has some number, and you can store a subset of these. The idea is to store a subset of these guys in the cache, so that whenever the CPU requests for that page, the hope is that you already find it in the cache. And the idea is that this communication is fast, and communicating between CPU and this is very slow. Okay, or these communications are very slow. So how many of you have not seen caching before? Because I'm kind of assuming that all of you have seen. Oh, you've not seen caching before? Okay, good. Then I'll give a concrete example of this. Okay, so the kind of thing I'm thinking of is you have a memory that stores, that has pages, let's say, that are numbered 1 through 1, 3 to n. And the CPU requests So this is the memory. Assume the memory is fixed. Okay, and the requests are like, first you may want to read page 1, then you may want to read page 2, then 2 again, then 3, then 1 again, 4, 1, so on. Okay. So we don't know what this request sequence is. Okay, so you have a request sequence. And the goal is to, and let's say you have k equals 3, which means that in your cache at every time step, you can store 3 pages. And maybe I should have a new page. So goal is maintain at each step. Okay. And so as to incur the minimum number of what are called cache misses. So you may start with an empty cache, okay, and now you get a request for 1. You will move you'll move the first page from memory to the cache. So let's again recap. So you have cache of size 3. And requests equals 3. The requests are so what you would do is initially you will realize that you get a request for page 1. You realize that you don't have page 1 in your cache. Okay. You will fetch it from memory and maybe write it here. And then you get a request for page 2. Okay, so you will maybe write it here because you have some free space in your cache. And now you get a request for 2 again. You don't need to fetch it. Okay, so here I'm paying the cost of fetching. And here I'm good, I'm not paying the cost of fetching. And then I get 3. Okay, so 3 is not there, so I need to fetch it from memory. I can write it in the new slot. If I wanted, I could have removed one of these 1 or 2 and written 3 in that place. Okay, but I'm not doing that given I have space in the cache. Okay, so I'm just bringing a new thing. Okay, and now I'm asking for 1. This is already there, so I'm good. So now I get a request for 4. Okay, so this is where something interesting has to be done, right? So I've got to decide which of 1, 2, and 3 to remove. Okay, because I don't have 4 in the cache, I've got to get it, but there's no more space left in the cache. Right? So I've got to decide which one to remove. I could say, okay, I could do some kind of a first in, first out kind of a thing. So 1 came in first, so maybe I could say, okay, I remove 1 and write 4. Okay. So this required some space. But this is bad for us because just in the next step I'm requesting for 1 again. Okay. So then I'll have to replace something and get 1 in. So if I'm bad with it and I replace 2 and I write 1, then in the next step again I have to do this. Okay. So a clever way to have done this would be, the first time I see 4, I should have removed 3 and written 4 out here. Right? So that way the next 2 steps I would not have had a cache miss. Okay. So the right solution in this case, so if I had a sequence like this, solution is to say that we remove 3. So let's have t equal. Let's write the time step here. Time step 1, 2, 3 at time step 6. And yeah. Okay, so this way you would avoid two cache misses. Okay, so was there something in the previous ML class? Oh, okay. All right. So yeah, so this is how you can avoid two cache misses by just evicting the right person, by evicting the right page. So everyone clear with this example? So right, and so now the question is, how do we decide this eviction policy? So how do we decide which page to evict? Okay, evict is the page. I mean, it's the page that you want to remove, right? So which page to remove when you get a request for a new page and your cache is full. So, all right. So this is the goal in caching. Okay, so we don't know what is going to come in the future, okay, but we've got to figure out which page to remove. Okay. And the goal in these kind of problems, this is always the goal in online algorithms, is you want to be able to compete with the optimum in hindsight. Okay, what do we mean by that? So this is, imagine a person who comes in after all the requests have been made. Okay, so there's always, this often happens, right? There's one person, or you look at all the sequence in hindsight and then you think, okay, I should not have evicted these pages because of those I'm incurring all these losses. Okay. So analysis in hindsight is often easier, right? So, but the goal in online algorithms is to be able to compete with the optimum in hindsight. Okay, so you don't want to do too much worse than the best possible move in hindsight. Okay. And you may wonder if this is even possible, right? Like, how am I going to compete with something I don't know, right? Like, I don't know what the requests are going to be, and so is it even possible? This is one question. Okay. For some problems, it is not possible, but we will see examples where you can say something interesting. And this notion, the ratio of cost of the given algorithm divided by cost of the optimum in hindsight, this is called the competitive ratio of this algorithm. So the algorithm itself just sees things one by one. It has no idea of the future, and it incurs a certain cost. You want to compare that cost with the cost of the optimum procedure in hindsight. So we'll see an example of this. So we'll actually work this example out so that you will actually see what's going on. And that's the definition of the competitive ratio. So let's see a simpler example and then we'll return to this. Okay, so a toy example, this is something, many of you might have seen this puzzle, right? So it is, suppose you are at the origin and you are on a line. And so this used to work well in Princeton where there was there's only one street on which all the restaurants were lying. But I don't know if it works here, right? So suppose you have a line on which all the restaurants are there, okay? And you are at the origin. Okay? You don't know which side of the origin the restaurant is. Okay? So and you don't know how far it is on the line. Okay, so the restaurant is just somewhere. Okay, so this is the restaurant. Now you've got to decide which side to move, and you are free to move however you want on this line. And okay, so you can move here, you can do something complicated. Yeah, so you are free to move however. And the point is we don't know restaurant is. Okay, so which side, how far? So if I knew which side the restaurant is, then I kind of know I just can go and I can find the restaurant wherever it is. Right? But the point is that you don't know which side the restaurant is. And what is the goal? Goal is not walk much more than this distance, right? So the optimum distance, if you knew where the restaurant is obviously this D, but you don't know what this D is, right? So not walk much more than D. Okay? So this is the goal, right? So how would you solve this problem? Like you have no idea what D is, and you're allowed to walk, however. Now you could say, a natural strategy would be, okay, I go right and hope that the restaurant is there. That will not work. If the restaurant was right here, then you end up walking for a long distance and you don't see anything, right? You have no idea what D is. Okay? So how would you go about solving this problem? Let's say I told you D was an integer, just to make things simple. Is this question clear? Yeah.
Well, you could choose a side and just walk D and see if you get there.
You don't know what D is.
Uh,
Yeah. So that's the problem. Yeah. If you knew D, that's what you would do, right? You would pick some side, walk D. Otherwise, you go the other direction. You would probably walk 3 times D total, and that's not so bad. How would you do it if you didn't know D?
Take small steps in the direction and return to the origin.
Okay, so that's a good idea, right? So what he's saying is, let's take a step of a certain size. If you don't find it within that distance, maybe come back and try to see if you can do some kind of search. But how would you formalize it? How much of a step size would you take? And this is what one would do in practice, right? You would explore a little bit, then you realize, oh, it doesn't look like the restaurant is on this side. Then you go the other side. Yeah. Sometimes you just feel like, okay, I can't find it, and give up, right? But yeah. But is there a way of doing things so that you don't walk too much more than D always?
That should be the lowest value possible. So
Alright.
step size should be modified.
Yeah, so you could initially walk, but what is the algorithm you're suggesting?
Just take one step.
Okay, so take one step to the right. Let's assume that distance is I assume distance is an integer, right? So you could go firstly at distance 1, say if it's at distance 1 on the right. Suppose it's not, what do you do?
Take 2 steps.
Okay, so this is promising, right? So what he's saying is, first start off early, so go distance 1 to the right. If you don't see the restaurant, then you want to go 1 to the left. Okay, suppose you don't see this here, what do you do now? Okay, so now you could say, okay, I go to 2 steps on the right. Okay, so I go to 1, -1, and now I explore, I go to like -2 out here, and maybe go 3 and so on. What's the total amount of walking you're doing like this? Suppose you're at a distance D. No, right? Because you're walking 1, I'm walking 1 plus 2 plus, then to get to this 2 I'm walking 3, and then to get to this I'm walking 4, and then I'm doing this until something like 2D. Okay? And this is something like D squared, right? So this is 2D squared, roughly speaking. So, and this is quite bad if D is big, right? You want to work at roughly D. So is there a better way of doing something like this? But this is a good idea, right? So you want to cover your bases. You don't want to miss the restaurant, so you kind of slowly increase your search thing. So is there a better way of doing this kind of exploration?
Instead of going like 2 on the right, that is going 2 on the left, and 2 on the left, 2 on the right. And then you have to take, like for the second one, you have to take 1 step and then 4.
So can you say that again? So you want to start with,
You are like taking like 1 and then we are going to -1 and then we are going to
okay.
You just go to -2 and if it's not there,
So you're saying first go to 1 as before. This is 0. First go to 1. Then go all the way to -2. Okay. And then what do you want to do if it's not there?
then we could like then go to 2.
So you want to go to 2 or okay. And then what?
And then we could go to, like instead of 2, we could go to 3.
Okay, so you're on the right track. So you're saying that on the right, maybe I won't go to 2, maybe I'll go to 3 and hope that the number of steps is smaller. But is 3 the right thing? Do you want to do something else? You guys are on the right track, yeah.
Can we start on one side, like we go on like, let's say 10 on one side,
Okay.
and then if there is no restaurant till that point, we go back to 0. I mean, we go to -10, like increase.
Yeah, so you could increase the step size of this essentially. That's what you're saying, right? So instead of 1, I go to 10.
Yeah.
So yeah, you can play with this as a trade-off. Okay, so you will see that if I do like k steps out here and then go to 2k out here, then if the optimum distance was 1 on the left, then you incur a ratio of k. Okay, so the ratio you get will be something like the max of d squared by k and k. Okay, so that will be the comparative ratio, because this d square will now reduce to d squared by k if you did a k type thing. And on the other extreme, and if it was just on -1 and you went all the way to k, then obviously you've got to, I mean, you lose a factor of k, right? So you can do this trade-off and you'll realize that maybe it's d squared by k squared. But yeah, so you'll see a trade-off, but it will still increase with d. Okay, so maybe it's d squared by k squared, and but it will still increase with d as you'll realize. Is there a way to avoid this d? Yeah.
Double the steps, so we move 1 and then do another step, 4.
Yeah, so that's the nice thing you can do, right? So what you can say is, I try to do some kind of a binary search. Okay, so what you do is you say, okay, I'm going to do 1 here, I'm going to do -2. Okay, so I'm going to go to 1, then to -2, and then to +4, and then -8, and so on. Okay, so this is something like what she was suggesting, but the key thing is to do some kind of doubling of the length. And you can show actually that this process is will have a competitive ratio of 3 or something like this. Okay, so I forget what it is exactly, but it will be a constant, because if the right answer is D, okay, so one thing you can be sure is that you won't go more than 2D or something like this. Okay, so the step you end up with at the right won't be more than 2D. Okay, so yeah, like in this example, okay, maybe the ratio will be more than 3. So for example, if in this case, suppose the right distance was a little bit more than 1. then you know that you are in bad shape, right? Then you are essentially traveling something like 7, but I think that's the worst that can happen. So it's a simple exercise for you. I won't go into the detail to show that this is actually a constant. Factor of from the optimum. Okay. And this is like a small constant factor. I mean, you can work it out. It'll probably be like 4 or something like this. So it's but the point is that this repeated doubling is a nice way of doing it. Okay, so you first go 1, then you go 2 on the other side, and so on. 4 on this side, and so forth. So this is one way to do this. Alright. So the other example, which many of you will face soon, is whether you want to rent or buy skis. Right? So most of us have no idea how often we are going to go, because it depends on too many unpredictable things like the weather, your laziness, and things like this. So we need to, we have no idea how many times we're going to go. And the question is, so renting may cost, let's say renting costs something like 50 and buying costs 500. So if you knew you were going to go 10 times, then buying obviously is the right thing, right? So if you're going to go more than 10 times, buying is clearly the better thing. But if you're not, if you're not sure, let's say you only go a couple of times, then obviously renting is better. So so the question is, how do you solve this sort of a problem? Like every time you go, you've got to make a choice, right? You either have to go pay upfront and buy the skis, or you just have to rent them for that one use, right? So how would you do this so that you don't feel too happy, too bad at the end of the day, like at the end of the season, let's say? Is there a good strategy for these kind of problems?
What are the factors that you can consider?
Sorry?
Like, what are the factors that you can consider apart from like?
Oh, let's say you don't know anything, right? So you have, that's the thing about online algorithms. They're a bit pessimistic in what you assume about the input. Okay, like in real life, you can say, okay, I'm going to motivate myself and stuff like this, but you assume that okay, you don't know anything about how many times you want to go.
We only know what rents and these prices.
Yeah, we only know these prices, and you want to make sure that if you that whatever you do, so at the end of it, your best solution in hindsight should be better. I mean, what you do should be not much worse than the best solution in hindsight. Okay, so that's always the goal, right? So the goal is low competitive ratio. And this is cost of algorithm divided by cost of best solution in hindsight. Okay, so how would you do it? In this case, trivially buying is always, buying the first time you go is one solution that will have a ratio of 10. Right, because the ratio of the cost is 10. But can you do better than that, or can you do significantly better than that? Is the question. And you might say, okay, I'm going to rent a few times and then buy. In which case, how many times should you rent? Is the question. So, what do you guys think?
Like if you rent for first time and then you rent for the second time, if the difference between the number of days difference between them is like close, if you go in twice in a week, so you might consider buying that, like you might go for the whole season, something like this. Like if you are going twice in a week for the first 2 times, so it might be possible that you might go again.
Yeah, so you're saying that, okay, I have some temporal thing. So again, you're using this context, right? So okay, in some sense, I want you also to be abstract. So you don't know whether it's twice in a week or something like this. So, but you're right. In real life, this is what you would do. You would actually use the context of
assumption that it snows at least once. Otherwise, you wouldn't consider fine.
Okay. Okay.
So you at least go at least once.
Yeah. So the first time you go, you do something, right? So you have to, I mean, you make a decision only if you go, right? So if you don't show up, then there is no decision. Okay, so you assume that. I mean, I guess you could order skis online, but that's not what we're doing, right? So we're just thinking of showing up and actually buying or renting. So. So any more? So there's actually, yeah, so it turns out, maybe this is not the best example, but this sort of problems arise a lot, and there's a pretty common solution to these kind of things. So that's what we're going to see. Okay, and so the idea is you want to rent a few times and then buy, right? Because you can't keep renting, because who knows, you end up going like 50 times and then you're like way off from the optimum. So always renting is bad. Okay, so you want to buy at some point. So what this suggests is that you rent for some t steps, for some t times, then buy at t plus the t plus first time you go. If t is 0, then it's like saying buy at the first step, right? So this is what we want to say. So for some t bigger than or equal to 0. Okay, so any reasonable solution would look like this. And in some sense, what we are asking is, what is the, what is the best t for this problem? So let's see, right? So let's suppose you rent for t times, buy at t plus 1. Then what is the competitive ratio? So it's cost of algorithm divided by the cost of the best solution in hindsight. Okay, so, and for this you've got to ask, how many times did you end up going? Right? So if you knew the number of times you ended up going, then you can clearly evaluate, then you know what is the optimum cost. Right? Because if it's more than 10, it is this. So let's assume that n is the number of times you ended up going. Because you want to always compete with the best algorithm in hindsight. So in this case, if, so this is what you're going. So what is the cost of the algorithm? Yeah, so it depends on whether n is more than t or not. Right? Because t was something that you just came up with as a strategy. So what you do is, okay, so let's write two expressions. Okay, so case 1. So I have a slide for this. So let's do this. So case 1 is n is more than t. Yeah, bigger than or equal to t. Let's do strictly more so that you actually end up buying. So n is strictly more than t. So in this case, you know that the cost of the algorithm is 50 times t plus 500. So this is what the cost of the algorithm is. And cost of optimum is, what's the cost of the optimum? So it's min of whatever, right? So it's not, yeah. So it's min of 50 times n and 500. Okay. So that's the cost of the optimum. Okay, so this is in the case when n is more than t. Okay, and now you have this ratio which depends on what this t is. So let's worry about the ratio in a bit. Let's write the second case. case 2, n is less than or equal to t. In this case, our cost is very simple. Our cost is just 50t. So, sorry, 50n. And cost of optimum $500 again. So which case do you intuitively think is a problematic one? The first or the second? Yeah, intuitively it's the first one, right? Because there is this plus 500 that you have, and you don't know what. But of course, you've got to analyze both. That's just intuition, right? So any question? So all right. So this is what we have. Okay, so the question now is, what should t be so that no matter what n is, the ratio is small? Okay. So t is something that I need to pick, right? So we have to figure out what t should be. Okay, because our strategy is rent for t times and buy at t plus 1. The question is, what should t be? So that's something like that. So now we have everything, right? So if, like suppose I told you, what is the competitive ratio for t equals 3? You can actually go and evaluate it. Right? And how would you do it? You'll first look at this case, and you will have some values out here. And then you will have some values for this case. Okay. And this is how you would solve this problem. Okay. So any questions?
Do you need to know n as well?
We don't know n. We don't know n. The point is that it should work for any n.
Okay.
So right. So that's a good point. But we don't know what n is. So yeah. So that's for this reason. Let's take example of t equals 3 and evaluate what this is. So then the second case is actually very simple, right? So if n is less than or equal to 3, then that is 50n and this is also 50n. Okay, so the competitive ratio is 1 in this case. Okay, so this case is so case 2 is 2 ratio is 1. What about case 1? Depending on n, it could be bad, right? So in that case, so our cost, if n is more than t, is more than 3 in this case, is something like 150 plus 500, and you want to divide by the min of 50n and 500. And for this, if n has to be more than t, to make this ratio as bad as possible, n has to be as close to t as possible. And so n has to be essentially 4. So you'll realize that, okay, so 200, but divided by 200, this is a pretty largish ratio. This is, I don't know what this is, but this is definitely more than 3, right? It's like 3.25. It's still not so bad, right? So even for t equals 3, you've got a ratio of something like 3.25. So what this means is that no matter what n is, I'm not worse than some 3 times the optimum. So, okay, so this is what you get for t equals 3. Then you can say, okay, what happens if I increase t a little bit? You can work this out. You'll see that the ratio kind of drops until a certain t, and then it starts increasing. Okay, and turns out that the sweet spot for these things is, I mean, in this case, it turns out t equals 9 is the best possible. Okay, so what this, I mean, for these numbers, right? So what it suggests is that you rent 9 times, and the 10th time you buy. And the 9 is just a consequence of the fact that 500 is 50 times 10. Okay, so this is, and in this case you can show that the ratio is actually less than 2. Okay, because if if the number of times you end up going, the n, is anything less than 9, then you are actually optimum. If it's 10, then okay, then you've paid 9 times 50 plus 500, and the optimum is actually 500. Okay, so in this case it's like 1.9 is the ratio. Okay, so you can actually show that the worst, that if I end up setting t equals 9, then the worst comparative ratio is something like 1.9. And the point is that this is less than 2. This is actually a pretty general phenomenon in these kind of problems. When you have to make this kind of renting or buying, it turns out that the best thing to do is to rent until you've lost a total amount of money that equals the cost, that the amount you need to buy, and then end up buying. Okay? You might say, okay, I'm losing a factor of 2 here, but that in some sense is the best you can do. Okay, so you can actually prove that you can't do anything better than 2 in this case if you have no knowledge of the future. Okay, if you have no knowledge of how well you're going to do, then the factor 2 is actually something you can't beat. So this is actually pretty optimal. And this, so it's not just true in this example. In general, you've got in these rent and buy problems, you rent until you've spent a total of what it costs to buy, and then you end up buying. Okay? And that often has a factor 2 associated with it. So is the idea clear? So these calculations are not, I mean, the reason I did this is because I wanted to show you how one might actually think about this, right? Because usually you just see this solution that you rent for 9 times and then buy. Then it's easy to verify that that's a factor 2 ratio. Okay, but how did you come up with the number 9? So you try a few things. The way you try these things is by writing these expressions. So this is what you've got to do. So any questions on this example? Alright. So now let's get back to caching. Okay, because so these are a bit of toy examples like walking on a line, skiing, and so on. So let's look at what what we started with in some sense. So this is the problem where you have k pages of cache. Okay. And if you recall, we had a request sequence. Okay. And we had a large memory. Okay, and the goal is to minimize number of cache misses. So one, all right. A different slide for that. So what is one natural algorithm you can think of for this? So this is something people kind of used to do all the time. It's a very natural algorithm, right? So you might say, oh, I fill up these pages based on the references. So let's say based on the requests. Okay, so you start off with an empty cache. So you initially fetch whatever pages that are requested. And the next time I see something new that's not there, I remove the first one, do some kind of round robin. Sorry?
I'm sorry.
Yeah, so you do some kind of round robin, right? So you just say, okay, I clear the first page of my cache, load the new thing, next time maybe I do the second page and so on. So the natural algorithm is round robin. This turns out to be really bad. Okay, so you can come up with examples where actually if you have some n things, you lose a function of n. Okay, so for really bad. So there are examples in which for a request sequence of size n, the comparative ratio grows with n. Okay, so it's with some constant time there. So this is quite bad. And you can see examples of this too, right? So I don't know if I should go into this. Yeah, let's skip the example. But if you play with this a little bit, you'll realize that I mean, in some sense, I could. I mean, maybe I should not have just been aggressive and evicted one, okay, because maybe one. Yeah, so you will see examples of that easily. So you can have comparative ratios that grow with n. Okay, so that's the point. If you do something like this. Now, something that people use often in practice. Okay, so it is what is called the LRU algorithm. And how many of you have seen this before? Okay, so this is called the least recently used algorithm. There is a least recently used. And the idea here is, you look at the request sequence. Okay, so let's say the request sequence was 1, 2, 3, 4, 1, 2, 4, something like this. Okay, and let's say your cache size was 3. Then initially you do what we've been doing before. So you see. So you load 1 into the cache, load 2 into the cache, load 3 into the cache. And once you see 4, you look at the cache and you say, and you look at what time each of these things was written, okay, or each of these things was accessed in some sense. So this one was accessed at t equals 1, this one was accessed at t equals 2, this one was accessed at t equals 3. Okay. So you evict the number that was least recently used. So in this case 1. So you remove this and write 4 here, and you say that at t equals 4, I have accessed 4. And now I get 1 again. So this is somewhat of a bad sequence, right? So I get 1. Now I look at the timestamps. I see that 2 was accessed only at t equals 2. Okay. So I remove this guy, and I update this to 1, and I write t equals 5. Okay. But now things start to become a little bit better. Okay, so now, okay, not yet. I guess. So I see 2. Then I end up replacing 3 because 3 was the thing that's got to be replaced, that was the least recently used. So I remove this, I write 2 here with the timestamp of t equals 6. But after this I have some decent period, right? So I see 1 is already in the cache, nothing to do here, and maybe 3 is not there now. Yeah, okay, so this is what you do, but this is the algorithm. Okay, so at every step, you look at the least recently used, and you remove that from the cache. In practice, this actually works much better than what this example suggests. So, because very often in practice, your cache size is not too small, okay? And you will end up actually reusing things that you've used in the immediate past. Okay, so you will end up having requests that look more like 1, 2, 3, 1, 1, 2, something like this. Okay, and if you've not seen something for a while, chances are you won't see it in the near future. Okay, so that's the idea behind this LRUL. So, okay, so this is the algorithm. Okay, so at every step, if we have a cache miss, whenever we have a cache miss, rather, whenever there's a cache miss, evict the page that was least recently used. Okay. That is a page whose last access was as far out in the past as possible. Okay, among all the elements in the cache. All right. So this is this algorithm. It's a very simple algorithm and it works reasonably well in practice. Now the question is, how good is it, right? So can we bound the comparative ratio of LR? So we want to say that LRU is not more than some factor times the optimal caching strategy in hindsight. So note that the optimal caching strategy will also have to have a bunch of misses, right? You can't always, like if I have a cache of size 3 and I have 1, 2, 3, 4, I've got to have at least one cache miss or a bunch of cache misses, right? So that's kind of what we want to trade off, right? So we want to see compare the number of cache misses LRU has to the number of cache misses the optimum has to have. And the question is, how do you do this bounding? So let's see. First, actually, let's see some bad news, right? So let's look at a lower bound. I want to claim that if you have a cache of size k, then you can't do better than a factor k. And this is it's an unfortunate thing for LRU, but we will see that it's not just LRU. I mean, slow bound holds for any deterministic algorithm. So this is like the bad news. And the point is that for LRU, there is some sequence for which the algorithm is a factor k worse than the optimal thing. Okay? And remember, k is pretty big, right? So k is the size of the cache. Okay? So we are actually saying that this is quite bad. And the example for this is actually very simple. It is what you would expect. Okay, so let's assume that there are so you have a cache of size k. And assume that there are k plus 1 pages total. So there's k plus 1 pages, possible pages, and you just request them. So initially you request 1, 2, 3 up to k, and then k plus 1. Now, if this is, LRU is doing something, so it's going to, it's going to remove this guy. And now you request 1, okay, and then it's going to replace 2, and then 2, 3, so on. So if you do this, if this is your request sequence, then it's clear that LRU is going to do very badly. But what is the optimal sequence for this? Okay, so the sequence is very simple: 1, 2, 3, up to k plus 1. Okay, so what is the optimal strategy for this? Yeah, so you can do this very kind of a naive strategy where you just say, okay, I have 1, 2, 3 up to k, fill it as usual, and then I get k plus 1, and I remove this guy, put k plus 1, okay. And then for 1, 2, 3 up to k, I am good. So here I encounter a miss. Okay, now I am good up to this point. Maybe here I encounter a miss, but I replace. So then I've got to replace something with k. Maybe I do k minus 1 with that. Okay. So throughout k minus 1, put k there. Okay. So you realize that this is roughly a factor k better than LRU. Okay. And the point is that you will have stretches of length k where you won't have a without any miss. So you'll have a stretch of initially this 1 through k, 1 through k minus 1 you do not have a miss, then the kth time you'll have a miss. Okay. So this makes an error roughly 1 out of k times, while the original thing makes an error each time. Okay. So that's the reason there's this factor of k. So this optimal strategy, this has a error which is, so that's how you think. Okay, so 1 out of k times you incur a cache miss, while LRU has a cache miss at every single step. Okay, so the ratio is k. So it's a little bit of a tricky argument, so I'll pause for a bit and see if you guys have any questions on this optimal strategy. Alright, so this shows that for LRU you can construct a sequence for which the optimum is a factor k better than what this achieves. And it turns out that this lower bound is not just for LRU. So in fact you can show that no deterministic cache replacement algorithm can have a comparative ratio better than k. And this is an unfortunate thing. Okay, so and the proof is actually very similar to what we've done. Okay? So you just have k plus 1 things, and any deterministic thing, maybe it's not going to replace 1, but it's going to replace some other thing. And when I see k plus 1, it might choose to replace 3 for some weird reason. Right? So it might choose to replace 3. And then I request for 3 here. Because it's a deterministic algorithm, when I'm constructing the sequence, I know what the algorithm is going to reject. So in that sense, I can always trick this deterministic algorithm. Right? Because I know what it's going to throw away, so I ask for that, and I know what it's going to throw away next, so I can ask for that and so on. Okay? And you can always show that there is an optimal strategy which only throws away things 1 out of k times. And that, so that again is a little bit of a tricky argument. You've got to say that I look into the future and throw away the thing that's going to appear the farthest. Okay? And so let's not go into that. But there is a very reasonably simple argument that shows that no deterministic algorithm can have a comparative ratio better than k. So I will post link to some lecture notes where you can read about this. So, but if you look at this lower bound, you realize that you are really using the fact that you can trick the algorithm every time, right? Like you know what it's going to throw away. Okay. And so it turns out if you allow randomness, okay, so this is one of the very cool facts, which is that about these kind of randomized methods in this space, which is that if the adversary doesn't know what you're going to throw away, all it knows is that, oh, you're going to throw away something with certain probabilities, then he can't actually fool you too badly. Okay, so you can show that simple randomized strategy actually achieves something like a log k factor in expectation. Okay, so so you can define what is called an expected comparative ratio, and this is expected. Okay, so with good probability, you won't be more than like something like a log factor away from the optimum. So this is pretty nice. And, yeah, I realized when I was making these slides that I don't know what this algorithm is. Okay, so I know it's somewhat simple, but I don't remember what it is. Okay, so yeah, but it's a nice fact to know. All right, so now let's look at the upper bound, right? So we've shown that LRU has a factor that is, it can be a factor k off from the optimum. Question is, could it be like 2k off? That is k the best possible. So that's what we're going to show. So it turns out that k is that, but it's not too much worse. Okay, so the theorem is that LRU is has a comparative ratio less than or equal to k. So this is so in some sense this is tight. Okay, so no deterministic algorithm can do better than k, and LRU is a deterministic algorithm that achieves k. So in that sense this is nice. Okay, and how would you prove something like this? So the challenge here is as always, like, how do you show that the optimum also makes a fair number of mistakes, right? So we want to show that cost of that for all request sequences cost of LRU divided by cost of optimal strategy for that sequence is less than or equal to k. Some sense, so that's like saying cost of optimal strategy is at least the cost of LRU divided by k. Okay, so how do you prove a statement like this, where you want to where you want to in some sense lower bound the cost of the optimal strategy? So this is the usual, this is the problem in arguing about comparative ratios, right? Like you want to show that the optimum can't be too good, right, compared to what your algorithm is doing. But you have no idea what the request sequence is, and you essentially have no idea what LRU is doing, right? Because you don't know what the request sequence is. You want to prove this for every sequence. So this is often the challenge, right, in analyzing comparative ratios. And so it turns out in this case there is a very clean argument. Okay, so let me give you the argument because it's hard to come up with it. So at least I don't know of a natural way to come up with it. Okay, so yeah.
In lower bound, we prove that LRU algorithm has a comparative ratio of factor k, and for the lower bound.
Yeah.
So for upper bound also, like we are saying that it's less than equal to, so is it exactly?
So, yeah, so that's the thing, right? So, it's not always k. So, what does it mean, right? So, here we are saying that, so the load bound is just one particular instance, right? So, for this instance, I've shown that it is k, right? That the commutative ratio is k.
Okay, but it can be better.
So there could be sequences for which it's way better, right? So in fact, in practice, LRU is pretty good, right? So, but what we are saying is that we are looking at the worst case thing. We are showing that it's k. Yeah, I mean, we showed that it could be at least k. And now we are saying that that worst case is actually the worst case. Okay, so in some sense, nothing could be worse than that. Okay, so that's what we are showing. So we want to show that for any request sequence, cost of LRU divided by this is less than 2. And this is done by a somewhat sleek argument. So what you can do is, let's look at the request sequence. Okay, so let's call it, first I get a page N1, N2, N3, and up to N capital T. Okay, so I run for capital T steps. And suppose these are the things that are requested. Okay, so that's like the sequence we saw here, right? Like 1, 2, 3 up to k plus 1. Right? So if you run for t steps, we always think of t as tending to infinite. Okay, so that's what we are interested in. So you get a huge long request sequence. And the idea is to say that is to divide this sequence into a bunch of blocks. And so the idea is divide sequence into blocks. Okay. And how do you divide them into blocks? You look for the maximal sequence starting at the current place. Maximal sequence that has less than or equal to k distinct requests. Okay, so what do I mean by this? So let's take a very simple example. Okay, so I take 1, 2, 1, 2. Again, k equals 3. 2, 3, 4. So you start from the left, okay, and you look for the maximal subsequence until which you've seen at most 3 distinct requests. Like in this case, until this point, I've only seen 2 distinct requests. Right? I've only seen one or two. And now you look, and then I see 3. At this point, I've seen 3 distinct requests. Here I'm seeing 4, right? But until this point, I have seen at most 3 distinct requests. So this is going to be my first block. Okay, so this is going to be my first block. Maximum subsequence starting at the beginning. And this is going to be my first block. And then I start from scratch. Okay, so I look at this thing. So I have got these guys. And let's again go back to this example. something like this, right? So I have a sequence like this. So this was my first block, and now I restart this process. Okay? I forget about everything I've seen in the past, okay? And I'm going to do this thing where I'm going to say, oh, okay, I've seen one distinct thing, now I've seen two distinct things, three distinct things. Again, it's three, and until this. Now I'm going to see the fourth one. Right? So this is going to be my second block. So the second block completely ignores construction of the second block. Completely ignores the first one. Okay, so this is how I want to divide into blocks. Okay, so I start at the beginning. I look for the largest subsequence where I see at most three different things. That was this. I identify that block. Just kind of forget about it. Now I pretend that my sequence starts here. Okay. I now look for the first time I see three, for the longest time for which I can see at most three different things. That's until here. Now I'm seeing the fourth one here, right? So that's why I stopped here. This is my second block, and then I forget about the whole thing, pretend that my sequence starts here, and look for the next block and so on. So, any questions on how this division into blocks is going on? I guess the only tricky thing is that you forget about everything you've seen in the past and you start afresh. Okay, so pretend that the sequence starts here. And now look for the longest subsequence that has at most k different figures. So, yeah, let me tell you the idea and then we'll come back to this. Okay, so why is this useful? The point is that in any block, LRU has at most k cache misses. Okay, and this is easy because this is a block in which I'm seeing at most k different things, right? So LRU might have had a miss every time a new thing was seen, but otherwise it would not evict stuff. So that's why it would have at most k cache misses. And then you can also show that at the start of a new block, any algorithm, even the optimal algorithm, has at least one cache miss. And this was because this was a maximal thing, right? So I went, let's look at the first block, right? So I went as far as I could go with at most k different things. I saw the k plus 1th different thing. The optimal algorithm has to throw out something that it has not seen before, right? So this is a new one. So the optimal algorithm must have had, maybe the optimal algorithm chose to bring in 4 at some point in the past. That doesn't matter, but in this interval, it must have had at least one cache miss, okay, one replacement that it has done, because it has had to bring in 4. So this is the general outline of this proof, that LRU has at most k cache misses in any block. Then you can say that at the start of a new block, opt has at least one cache miss. So if the number of blocks is some b and this b is large, then you can show that opt has at least b and LRU has at most k times b. Okay, and this shows that b is the number of blocks. Okay. It's a very simple argument, but it shows that it's very lossy, as you can see. That's why you get this factor k. But in some sense, that's the best anyway. So that's what you get. So let's stop here. But think about how these blocks are constructed. It's kind of a tricky argument. But this is how all these arguments are, because you've got to argue about an optimum you have no idea about, right? So you've got to have some trickery in that.